Okay, let's unpack this. Imagine you're standing at the base of a data mountain, right? Maybe for a new project, or maybe just driven by pure curiosity. It's vast, it's complex, and honestly, the sheer volume can feel pretty overwhelming. How do you find those like invaluable gold nuggets of insight without getting completely buried under all the raw material?
Well, that's precisely what we do here on the deep dive. Today, we're plunging headfirst into the fascinating and incredibly practical world of machine learning for predicting housing prices. And we're using a truly authentic, real-world data set from California to do it. Our mission today, it's really more than just understanding facts about housing data. We're going to walk you through the entire journey, the process that data scientists actually undertake to solve a problem like this. It starts with intimately understanding the raw data, then moves through building foundational predictive models, and culminates in the relentless, meticulous process of fine-tuning them, like getting the best possible performance.
By the end of this deep dive, you'll not only grasp the specifics of housing data prediction, but you'll also gain a powerful blueprint for how these sophisticated machine learning models are built, refined, and actually deployed in practice. It's really about empowering you with the how and the why.
Yeah, and what's truly captivating about this deep dive, I think, is that we aren't just presenting you with like a static report or some pre-baked solution. We're going to step through the dynamic, the iterative process itself, the thought process, the strategic choices, maybe even some of the moments of challenge and eventual triumph that really define how robust predictive models are constructed. You'll see why certain crucial decisions are made along the way, and perhaps most importantly, how to critically evaluate their effectiveness. It's really about gaining a deeper appreciation for the how and the why behind successful machine learning. So our journey today will begin by truly understanding our raw material, the California Housing Dataset. We'll delve into its unique DNA, so to speak. From there, we'll progress to building some foundational models, specifically linear regression, which will reveal the initial scope of our challenge. We'll then evolve these models with more powerful, more flexible approaches like polynomial regression, and crucially, introduce regularization techniques too. Well, keep them disciplined. And finally, we'll master the art, and maybe the science too, of hyperparameter tuning to squeeze every last drop of performance out of our models. This is really a comprehensive tour designed to leave you not just well-informed, but genuinely confident about the inner workings of predictive modeling in the real world.
Okay, so every great analysis, right, every groundbreaking insight, and certainly every powerful machine learning model, it really starts with getting intimately familiar with your raw material. You wouldn't build a skyscraper on a shaky foundation, obviously. And similarly, you can't build a robust model on data you don't fully comprehend. For us, that raw material, that foundational element, is the California Housing Dataset. So to kick us off, what exactly is this data? Where does it hail from, and what are its fundamental characteristics? What's its story?
That's exactly where we have to begin. The California Housing Dataset is it's a veritable classic in the machine learning world, and for good reason. It's a benchmark dataset originally obtained from the StatLib repository, which, for those interested in exploring various datasets, is actually a fantastic historical source. Now, a truly crucial detail to understand right from the start. This dataset contains aggregated data. We are not, and I want to repeat this, we're not looking at individual houses with their specific quirks and prices. Instead, we're looking at individual districts, specifically what are called block groups within California. Think of a block group as a small geographic area, typically with a population of maybe 600 to 3,000 people. It's used by the U.S. Census Bureau. So each instance, each row in our dataset represents a snapshot of the economic, social, and geographic characteristics of one of these block groups. This aggregation is really important because it means our predictions will be at the district level, not for a single home.
Right, so we're predicting the typical price for a whole neighborhood block, essentially, not Mrs. Smith's house on the corner.
Exactly. And in total, the dataset comprises 20,640 instances, or examples, each representing one of these block groups. For each of these, we have 8 numerical predictive attributes. These are the pieces of information we'll use to make our predictions. Plus, we have our single target variable, which is the value we're trying to predict, the median house value for that specific block group. And here's a bit of good news for anyone who's ever wrestled with messy real-world data. A very helpful characteristic of this data set, especially for initial processing, is that it has no missing values.
Oh, wow. It's rare.
It is. It simplifies things immensely, right? We don't have to worry about complex imputation techniques or dropping rows right away, which honestly can be a significant time sink in real projects. It truly sets us up with a nice, clean slate.
That's a huge advantage, yeah. I mean, I've definitely spent days just cleaning data before even getting to the fun part. So with this clean slate, let's unpack those 8 predictive attributes. What are they, and what kind of insights do they offer about these block groups that could possibly influence housing prices?
Absolutely. Each attribute provides a vital piece of the puzzle, and collectively they paint a pretty rich picture of the block group. Let's go through them. First, MED-IN-C. This stands for median income in the block group. This is, as you can probably imagine, an absolutely pivotal feature for house price prediction.
Yeah, that seems obvious. Wealthier areas.
Generally speaking, yeah, they tend to correlate strongly with higher property values. It's often one of the strongest drivers we see. Then there's house age. This represents the median house age in the block group. Now, one might initially think older means less valuable, but it's not always so simple. Older, more established neighborhoods might have different value dynamics than newer developments. Think of like historic districts versus newly built suburban areas. There's often a subtle interplay there.
Okay, so age isn't just a simple negative factor.
Not necessarily, no. Then, AV rooms. This is the average number of rooms per household within the block group. More rooms typically mean larger homes, right? Which can directly influence value. It's kind of a proxy for the size and spaciousness of the housing stock in that area. Average bedrooms. Similarly, this is the average number of bedrooms per household. Again, a very direct indicator of home size and configuration, which is, a key component of real estate value. Population. This is simply the block group population. Densely populated urban areas might have different housing market pressures, maybe higher demand, limited supply compared to more sparsely populated rural or suburban areas.
Right, density matters.
It can, yeah. AVG occupancy. This refers to the average number of household members. This can give us an idea of the household density within the block group, perhaps indicating whether homes are typically single-family or multifamily dwellings, or maybe even if there are more extended families living together, all of which could impact market dynamics. And finally, latitude and longitude. These are the geographic coordinates of the block. As anyone in real estate will tell you, it's all about location, location, location.
Right.
Geographic factors heavily influence property values. Being near desirable amenities, in a top-rated school district, close to job centers, or simply in a high-demand coastal city versus an inland agricultural region that can massively impact prices. These two features, when you combine them, are incredibly powerful. Now, for our target variable, the one we are trying to predict, median house value. This represents the median house value for each district. But here's a profoundly important detail. It's expressed in units of $100,000.
Oh, okay, so a 2 isn't $2.
Exactly. If the data set shows a value of 2, that actually means $200,000. If it shows 4.5, that's $450,000. It's absolutely crucial to keep this scaling in mind when interpreting our model's predictions. Otherwise, your predictions will be wildly off by a factor of 100,000.
Wow, okay. Yeah, that scaling is a critical piece of context. Forgetting that would lead to some seriously misinterpreted results. So once we have these attributes in our target, what's the very first thing a seasoned data scientist does to really understand their data better? I imagine it's not just staring at a raw spreadsheet of numbers. There must be a more systematic approach to really feel the data, right?
Exactly right. The next critical step is initial data exploration, often through a combination of visualizations and summary statistics. This isn't just a formality, it's more like a detective gathering clues, It helps us uncover hidden patterns, identify potential issues like outliers or strange distributions, and really importantly, formulate hypotheses about relationships before we even think about building a model. This initial phase is often where we discover those crucial gotchas. So when we look at histograms, which show the distribution of each feature, some really interesting insights jump out immediately. For MED-IN-C, median income, and house age, median house age, MED-IN-C shows what we call a long-tail distribution, meaning that while the majority of block groups fall within a certain income range, there's a smaller but significant number of block groups with substantially higher median incomes. This long tail tells us our model needs to be robust enough to handle these income disparities without being overly skewed by them. House age, on the other hand, is a bit more uniformly distributed, though it does show some noticeable spikes. These spikes might indicate maybe periods of rapid urban development or specific housing booms where many homes were built around the same time.
Interesting. What about the others? Rooms, population?
Right, for AV rooms, AVG bedrooms, population, and AVG occupancy. These features often reveal a very large range, with a small number of very, very large values. This strongly suggests the distinct presence of outliers.
Outliers.
Yeah.
Like extreme values.
Exactly. Imagine a block group with an unusually high population density, or perhaps a large, atypical community living arrangement that skews the average occupancy significantly. These extreme values can disproportionately influence a model if you don't handle them carefully, potentially pulling its predictions way off course. Latitude and longitude. Individually, their histograms don't reveal a whole lot on their own, but their combination is absolutely key for geographic pricing. When you plot them together, maybe with the house value as a color overlay, you can literally see clusters of higher-priced homes corresponding to specific desirable geographic regions, like coastal areas or major metropolitan hubs. It just visually confirms the old real estate adage.
Location, location,
You
location.
got it.
Yeah.
And then, for our target distribution, median house value. It also exhibits a long tail, indicating some very expensive areas, but here's a truly critical, honestly, maybe even shocking detail. It has a noticeable spike right at the very end of the histogram.
A spike at the end. What does that mean?
It means that all houses with a median value over $500,000 were explicitly truncated to a maximum value of 5, which represents $500,000.
Oh, what? Serious?
Seriously, this isn't just a detail, it's a fundamental ceiling on our model's intelligence. It means our model will never be able to predict or even distinguish a $600,000 house from a $1 million house or even a $2 million house. They all just show up as 5 foot in the data.
Wow.
This is a critical gotcha for anyone trying to interpret high-end predictions. It's not a limitation of our model per se, but a data source constraint that you absolutely must be aware of before deploying it. It essentially means our model can only tell us if a house is valued up to $500,000, not precisely how much above that it might be worth.
Wait, hold on. So if a block group's median house value is, I don't know, $750,000 or $1.5 million, the data set just says 5. That's a massive nuance. It completely changes how you'd interpret predictions at the higher end of the market, doesn't it? What does that mean for, say, a real estate agent trying to use this model?
It's a huge shift in perspective, isn't it? For that real estate agent, it means our model is probably excellent for the vast majority of the market, from entry level up to that $500,000 mark. But for anything above that, it essentially gives a binary answer. Okay, it's at least $500,000. It just can't differentiate further. So if you're trying to price a luxury home, this particular model just won't give you the granular detail you need. You'd have to find supplementary information or maybe even a different data set entirely. This data truncation is a perfect example of why that thorough data exploration is absolutely non-negotiable. It reveals inherent limitations of the data that directly impact the practical applicability of your model. If we hadn't spotted that, we might mistakenly promise ultra-precise predictions for high-value properties when the data simply doesn't support it.
That makes so much sense. Okay, so visualizations reveal the distributions, the truncation. What about just the raw numbers, the statistics?
Right. Beyond visualizations, descriptive statistics like calling the .describe method on the dataset in pandas are equally illuminating. This gives us a quick summary. Count, mean, standard deviation, min, max, and those important quartiles, the 25th, 50th, which is the median, and 75th percentile for each feature. For avgrooms, avdurbarums, population, and avjoccupancy, the statistics clearly confirm the presence of those outliers we spotted visually. By observing the truly significant difference between the 75th percentile and the maximum values. For instance, if the 75th percentile for population is, let's say, 2,000, but the maximum is 30,000, that's a massive gap. That strongly points to extreme values or outliers, and the sources confirm this difference is quite large in each of these features, signaling that we probably need to consider strategies to handle these extreme values later on in the modeling process. And finally, we often use pair plots. These visualize the relationships between every pair of features, and critically, each feature against our target variable. These plots really show that mediancy, median income, and that combination of latitude and longitude are consistently strong indicators of house price. You can literally see how higher median incomes tend to cluster with higher house values, and how specific geographic regions, especially coastal areas, show up as distinct high-value zones. This initial visual assessment, combined with the statistics, truly informs our modeling strategy. It points us towards the most influential features right from the get-go.
So let's recap where we are before we even think about a model. We have a data set that's, well, remarkably clean in terms of missing values, which is great. It's rich with clear predictive attributes like income and location, but it also possesses some really interesting and very important quirks, like that hard ceiling, the truncated target variable at $500,000, and the clear presence of potential outliers in features like population or average occupancy. These initial explorations, this deep dive into the data itself, they're absolutely vital, aren't they? They don't just provide facts. They highlight potential challenges and reveal inherent opportunities, guiding us towards more informed decisions down the line. It's like having a detailed map of the terrain before you even set out on your journey. Okay, having truly mapped out the DNA of our data, understanding its quirks and its strengths, it's maybe tempting to jump straight to the most complex cutting-edge algorithms out there. But a seasoned data scientist, as you said, always starts with the simplest tools first. So let's lay down our foundation with linear regression. It's the workhorse of many predictive tasks, a real foundational algorithm, and we'll explore two primary ways to train it. Why do we advocate starting simple? And what critical insights are we hoping to glean from these initial, seemingly basic attempts?
Yeah, starting simple is just, it's crucial because it gives you a fundamental baseline. You need to know how well the most basic model performs before you start introducing more complexity. It sets the bar for what good looks like, right? And maybe more importantly, helps us understand if our problem actually needs more sophisticated techniques or if a simpler solution might already be, reasonably sufficient. It's a diagnostic step, really. So a quick refresher on linear regression. Its goal is to predict a real numbered label, in our case, the median house value based on a linear combination of the input features. While it sounds deceptively simple conceptually, it's trying to fit the best straight line, or more accurately, a hyperplane in multidimensional space. Its true power lies not just in its simplicity, but often in its interpretability. It's our diagnostic tool, revealing how much each feature linearly contributes to the outcome. When we see it underfitting, it's basically telling us, okay, the world's not flat, there are curves and interactions we're missing. The model essentially learns weights for each feature, determining its contribution along with an intercept term. The core idea is just to find the weights that minimize the difference between the predicted and actual values, most commonly by minimizing the sum of squared errors. Now, before we even run our first linear model, an incredibly important preparatory step for many machine learning algorithms, especially linear models trained with iterative optimization, is feature scaling.
Scaling. You mean like making sure all the numbers are in the same range?
Exactly. Imagine you have one feature, say latitude, ranging maybe from 32 to 42, and another population ranging from 0 to 30,000. If you don't scale them, your optimization algorithm, especially one like stochastic gradient descent, would be essentially tripping over features. It would interpret a small change in population as far more significant than a large change in latitude, simply because its magnitude is so much larger.
Ah, I see. The big numbers dominate.
Precisely. The algorithm would spend all its effort trying to navigate the cliff face of the high magnitude features, potentially missing the subtle gradient of the gentle slope of the smaller magnitude ones. Using something like standard scalar from scikit-learn brings all features to a similar scale, typically with a mean of 0 and a standard deviation of 1. This isn't just a nicety, it's often crucial because it ensures that all features contribute more equally to the distance calculations and optimization steps. This leads to faster convergence, often better performance, and prevents certain features from numerically dominating the learning process. Scaling basically makes the entire landscape equally navigable for the optimization algorithm.
That analogy of navigating a landscape with cliffs and gentle slopes really brings it to life. It's like making sure all your measuring tapes are calibrated to the same unit before you start building. Makes total sense. So with our features properly scaled, let's dive into the first method for training a linear regression model, the normal equation. What makes this approach unique?
Right, method 1. The normal equation, often implemented through sklern.linearModel. Linear regression in Python is what we call a closed-form solution. This means it directly calculates the optimal weights for your model using a single deterministic mathematical formula. There's no iteration involved, no stepping through data bit by bit. You feed it the data, and it mathematically computes the precise best answer.
So it's like solving an equation directly.
Exactly. From a practical standpoint, this method is very precise, and for simpler models, it's straightforward to use. However, it has a significant computational implication that makes it impractical for many real-world data sets. It can be extremely intensive for a large number of features. The complexity is roughly OM2, where M is the number of features. What this means in real terms is that the computational cost grows by the square of M.
Okay, so double the features, 4 times the work.
Roughly, yeah. So if you have 100 features, it's like 100 squared steps, maybe 10,000 computational units. Double your features to 200, and suddenly it's 200 squared, that's 40,000 steps instead of 10,000. This quadratic growth is why the normal equation quickly becomes entirely impractical once your data set hits hundreds or thousands of features, let alone millions. On the upside, because it's a direct calculation, there's generally no need for hyperparameter tuning for the optimization process itself, which simplifies things if your data size allows for it. You just plug it in and get the optimal linear solution. When we apply the normal equation to our California housing data set, the mean absolute error, MAE, on the test set came in at around 0.527.
0.527. That's in units of $100 height, so about $52,700 off on average.
Exactly. Now, the training and test errors were quite close together, which is generally a good sign because it suggests the model isn't wildly overfitting to the training data. However, the error value itself, well, it isn't particularly low. An average error of over $50,000 is substantial. This often points to underfitting the model is simply too simple, too rigid to fully capture the underlying, potentially complex relationships in the housing data. It's trying to fit a straight line where maybe a clear curve or more nuanced pattern is actually needed.
Okay, so it's a good starting point, a basic map, but clearly not the final destination. The model is missing some of the intricate details and nuances. This sets us up for the next approach, which sounds a bit more dynamic: stochastic gradient descent, or SGD. What makes SGD different, and why would we opt for it, especially if the normal equation is so direct?
Indeed. Method 2. Stochastic gradient descent, SGD, implemented by Sklern.linearmodel.sgd regressor, is fundamentally an iterative optimization approach. Instead of calculating the optimal weights directly in one go, it gradually adjusts them by taking small steps. And here's the stochastic part. It calculates the error and updates weights based on just a subset of the data, often just a single example at each step.
Just one example at a time.
Yeah, or a small batch, yeah. This makes it incredibly efficient for truly large data sets, as its computational cost scales linearly with the number of training examples. That's a huge advantage over the quadratic scaling of the normal equation. For a data set with millions of examples, SGD can potentially complete its task while the normal equation might still be crunching numbers on just a fraction of the data. However, this efficiency comes with a trade-off. SGD requires careful tuning of multiple hyperparameters. You need to get the settings right. For instance, you need to set maxitter, which defines the maximum number of passes over the training data. A common heuristic is to set enough iterations so that the model effectively sees at least, say, 10 million examples. Empirical findings show convergence often occurs around 1 million examples seen. This isn't just an arbitrary number, it's about giving the algorithm enough looks at the data to settle into a good solution. Another crucial practice, especially for preventing overfitting and also saving computational resources, is early stopping. This technique basically stops training when performance on a separate validation set, a small part of the training data held out, doesn't improve for a specified number of iterations.
So it stops if it's not learning anymore.
Essentially, yes. For example, setting night or no change 5 with a small toll value, like 10 to 5, and validation fraction 0.1 means if the model's performance on 10% of your data doesn't significantly improve by that tiny toll amount over 5 consecutive checks, the algorithm just stops. It's a pragmatic compromise. You're telling the model, keep training, but if you don't show meaningful improvement over a short period, you're probably just overfitting to noise or spinning your wheels. Let's call it good and move on.
Definitely.
It's about finding that sweet spot where learning plateaus, ensuring we don't waste compute on diminishing returns or start memorizing the training data's quirks. And then there's a setting like average, true for averaged SGD, ASGD. This is actually quite a smart technique. Instead of using the weights from the very last update, the model's final coefficients are set to the average of the weights across all the updates during training.
Averaging them out smooth things.
It often does, yeah. It can lead to more stable solutions, smoothing out the oscillations that SGD can sometimes exhibit. It can even allow for slightly larger initial learning rates, which can potentially speed up the training process by letting the model take bigger initial jumps towards the solution. And like other gradient-based methods, SGD is also quite sensitive to feature scaling. Properly scaled data is absolutely essential for it to converge effectively and efficiently. So when we put SGD regressor to the test on the California housing dataset with just a basic setup, the mean absolute error on the test set was around 0.56.
0.56. It's slightly worse than the normal equation in this case.
Initially, yes, slightly higher in this untuned state. This is comparable to what we saw with the normal equation, reinforcing our earlier thought. Basic linear models, whether solved directly or iteratively, might simply be underfitting the problem. And for SGD regressors specifically, this initial, slightly higher error strongly suggests that its performance can often be significantly improved with dedicated hyperparameter tuning. That's a topic we'll definitely dive into with great detail shortly. It's a powerful tool, but like a finely tuned instrument, it really needs its settings adjusted just right.
Okay, so our baseline linear models, whether using the direct normal equation calculation or an iterative approach like SGD, they both basically show us that we're underfitting. The model isn't quite capturing the complexity hidden within the California housing data. It's like trying to draw a detailed landscape with only a single blunt crayon, maybe.
That's a good analogy.
This sets us up perfectly for the next big challenge. How do we give our models more tools, more flexibility to understand those subtle, nonlinear relationships that are clearly at play in real-world housing markets? How do we upgrade from that single crayon to a whole set of sophisticated art supplies? Right, so to move beyond those simple straight-line assumptions that our initial linear models offered, we clearly need to introduce a layer of sophistication. We can achieve this by giving our models more expressive power through something called polynomial features, and then, crucially, by keeping that power disciplined with techniques called regularization. It's about providing the model with a richer vocabulary, maybe, to understand the data's underlying patterns, but also ensuring it doesn't just memorize the training examples without truly learning the generalizable rules. Is that the idea?
That's a perfect way to put it. We're essentially teaching our model to see curves, interactions, and nuances instead of just straight lines and simple additive effects. Let's start with polynomial regression, capturing nonlinearity. The core concept here is quite elegant, actually, and surprisingly simple at its heart. You transform your existing features into higher degree polynomial terms. So if you have a single feature, say x, with a degree of 2, you might transform it into x and by 2. If you have multiple features, say by 1 and by 2, and you set a degree of 2, polynomial features in scikit-learn will create new features like by 1, by 2, by 12, by 22, and critically interaction terms like by 1 times by 2.
So it creates new features based on combinations and powers of the old ones.
Exactly. And the magic is that once you create these new polynomial features, you can then apply a standard linear regression model to these transformed features. Effectively, you're still fitting a linear model technically, but it's fitting to a nonlinear representation of your original data. This allows it to capture complex, curved relationships that a simple straight line could never approximate. It's like bending a ruler to fit the contours of a landscape. This is typically a seamless two-step process in practice. First, you apply a polynomial transformation using something like polynomial features. Second, you then train a linear regression model, either with the normal equation or SGD, on those transformed features. A key implementation tip, especially in scikit-learn, is to use a pipeline.
A pipeline, what does that do?
It allows you to chain these steps together seamlessly. For example, polynomial features followed by standard scalar, because scaling is still important for the new features created, and then linear regression. Using a pipeline ensures proper data flow, it helps prevent data leakage between steps, and critically, it ensures that scaling is applied after the transformation, which is the correct order of operations. It just makes your code cleaner, more robust, and less prone to errors. There's also an important nuance with polynomial features, the interactionally true parameter. If you set this, the transformer will only include interaction terms, like by 1 by 2, and explicitly exclude higher powers of individual features, like by 12 or by 22.
Why would you do that?
Well, it can be very useful when you suspect that only the joint effects between features are what you desire, for instance. Maybe the impact of house age on value only becomes significant when combined with med and C in a certain way, rather than house age having a non-linear effect purely on its own. It just offers more fine-grained control over the complexity you're introducing. So when we applied polynomial regression with a degree of 2 to all our features in the California housing dataset, the performance improved dramatically.
How much?
The mean absolute error dropped significantly to around 0.46 on the training set and 0.48 on the test set.
Wow. Okay, from 0.53 or 0.56 down to 0.48 on the test set, that's a big jump.
It is. Remember, our initial linear model was around 0.52 to 0.56 MAE on the test set. This was a clear, substantial improvement. It unequivocally indicated that introducing polynomial features indeed helped address the underfitting problem we saw earlier. It validated the idea that the underlying relationships in the housing data are fundamentally nonlinear, and our model was now better equipped to capture them.
That's a significant leap. It's like upgrading our crayon to a whole box of colored pencils, right? Allowing for much more detail in our drawing. But as you mentioned earlier, adding complexity, especially with polynomial features, can also introduce a new, formidable challenge. Overfitting. It's like giving an artist maybe too many colors. They might get lost in the tiny details and forget the overall picture. How do we keep our powerful new models from simply memorizing the training data down to its every speck of noise and then failing on new, unseen examples? This is where regularization comes in, right?
Exactly. Regularization. Taming overfitting, ridge and lasso, is our primary answer to that very real threat. While polynomial models are powerful and flexible, they do have a natural tendency to overfit. Overfitting, just to recap, means the model performs exceptionally well on the data it was trained on. It's practically memorized it, but then performs poorly on new, unseen data. It's learned the noise, not the signal. Regularization helps combat this by adding a penalty to the model's loss function during training. This penalty discourages the model from assigning overly large weights to features, effectively encouraging simpler, more generalizable models that are less sensitive to minor fluctuations in the training data. Think of it as a kind of quality control measure, preventing the model from becoming excessively complex or sensitive. Let's delve into two primary types of regularization. Ridge regression, L2 penalty. Ridge adds a penalty based on the squared magnitude of the coefficients. Imagine each coefficient is like a balloon. Ridge adds a cost to how much each balloon inflates. The larger the weight, the higher the squared penalty.
So it tries to keep the weight small.
Exactly. The effect is that it shrinks the coefficients towards zero, making them smaller and less impactful overall, but it rarely shrinks them exactly to zero. This makes it good for general smoothing and reducing the overall complexity of the model without completely eliminating features. It's particularly useful when you believe most features might have some predictive power, but you want to reduce the influence of any single one becoming too dominant. In scikit-learn, you'd use sklearn.linearmodel.ridge or maybe SGD regressor with penalty A2+. The strength of this regularization is controlled by a hyperparameter called alpha. A larger alpha means a stronger penalty, leading to smaller coefficients. Our initial test before tuning showed a mean absolute error of around 0.48 for ridge on top of the polynomial features. Slightly higher than the polynomial model alone, but the real power of ridge comes when we meticulously tune its alpha value. Lasso regression, L1 penalty. Lasso, on the other hand, adds a penalty based on the absolute magnitude of the coefficients. The key difference here is its profound effect. Lasso has a tendency to shrink some coefficients exactly to zero.
To zero, so it gets rid of features.
Effectively, yes. It performs feature selection as part of the process. If a feature isn't contributing significantly, Lasso can just zero out its corresponding weight, completely removing its influence from the model. This makes the model simpler and potentially more interpretable, as you can see which features truly matter according to the model. This is particularly useful when you suspect many features might be irrelevant or redundant for your prediction task. It's implemented with sklearn.linearmodel.lasso or SGD regressor with penalty all1, also controlled by an alpha parameter. Initial tests showed an MAE of about 0.52, higher than ridge initially, but again, this is before that critical tuning phase. And then there's ElasticNet, which offers a compelling combined approach. It's a convex combination of both the L1 lasso and L2 ridge penalties.
Best of both worlds, maybe.
That's the idea. It tries to balance the feature selection benefits of Lasso, where less important features can be completely zeroed out with the coefficient shrinkage and stability provided by Ridge. It's a fantastic middle ground, especially when you have a large number of features and you suspect some are redundant, but you also want the stability that L2 regularization provides. You'd typically use SGD regressor with penalty ElasticNet and an L1 ratio parameter to control the mix. For example, L1 ratio 0.3 would mean 30% lasso penalty and 70% ridge penalty, allowing you to fine-tune the exact blend.
Okay, this is great. We've successfully added both power through polynomial features to capture nonlinearity and discipline, through regularization, ridge, lasso, ElasticNet, to prevent overfitting. We're building far more sophisticated and nuanced models than our initial baselines. But here's the burning question that keeps coming up. How do we know we've got the right degree for our polynomial transformation? Is degree 2 always best? Or could degree 3 be better? Why not degree 10? And what about the perfect regularization strength, that alpha value for ridge or lasso? Or the ideal L1 ratio for ElasticNet? This isn't something the model just learns during its training process, right? It's a choice we have to make. This leads us directly into the absolute necessity, and indeed the art, of hyperparameter tuning. Hashtag Tachik for AV. The art of hyperparameter tuning, HPT. So what does this all mean for us? Getting the right balance in these now quite complex models, finding that elusive sweet spot between underfitting and overfitting, it just can't be guesswork, can it? It requires a really systematic approach to finding the sweet spot for these parameters the model doesn't learn itself. This is where the art, and maybe the science, of hyperparameter tuning truly shines. It's about unlocking the full potential of our carefully constructed models and ensuring they perform optimally on unseen data.
That's a fantastic way to frame it. Hyperparameter tuning is absolutely paramount for maximizing model performance and ensuring generalizability. Let's first maybe clarify what hyperparameters actually are. They are parameters that are not directly learned by the model during its training phase, through gradient descent or direct calculation. Instead, they are external configurations that you, the data scientist, set before the training even begins. Think of them as the settings, the knobs, or the dials that control the learning process itself, itself or even the underlying architecture of the model.
Okay, so give me some examples again from what we've discussed.
Sure. The degree in polynomial features you, the user, decide whether it's degree 2 or degree 3. The model doesn't figure that out on its own. That's a hyperparameter. Similarly, the alpha value in ridge or lasso regression, which controls the strength of regularization, is a classic hyperparameter. Even the learning rate strategy, like constant or adaptive, or the specific penalty type, L1, L2 elastic net in SGD regressor, are hyperparameters. The ultimate goal of hyperparameter tuning is to systematically find those specific values for these parameters that result in the best cross-validation scores, giving us the most robust and generalizable model performance across different subsets of our data. To perform a systematic hyperparameter search, you generally need 5 key components. 1, the estimator. This is simply the model you want to tune the regressor or classifier. It's the engine you're trying to optimize. 2, the parameter space. This is the precise range or specific set of discrete values you want to explore for each hyperparameter. For polynomial degree, maybe you try integers from 1 to 5. For an alpha value in regularization, you might define a logarithmic range like 0.0001, 0.01, 0.11, 10. Defining this space is often an iterative art itself, starting wide and then maybe narrowing down. 3. The search sampling method. How do you intend to explore that defined parameter space? Do you check every single combination exhaustively, like a grid, or do you intelligently sample from it, like randomly? This is where strategies like grid search or random search come into play. 4. The cross-validation scheme. How do you robustly evaluate performance across different data splits to avoid making decisions based on, like, a fluke performance on one particular split? This involves dividing your training data into multiple folds for repeated evaluation. 5. The scoring function. This is the objective metric used to evaluate model performance during the tuning process. For regression, it might be negative mean squared error or negative mean absolute error. We often use negative forms of error metrics because most tuning algorithms are designed to maximize a score, so minimizing an error is the same as maximizing a negative error.
Okay, so it's a whole strategic setup, not just randomly trying values and hoping for the best. You mentioned data splits again earlier. This is often a point of confusion. How exactly do we divide our data for hyperparameter tuning to ensure we're getting a truly unbiased view of our model's performance? What's the protocol for keeping our final evaluation honest?
This is one of the most vital aspects, honestly, and it's where many practitioners, even experienced ones, can make critical mistakes if they're not careful. For robust hyperparameter tuning and, crucially, an honest final evaluation, you absolutely need crucial data splits. Training set. This is the data used to actually train the individual models for each hyperparameter combination you're testing during the tuning phase. The model learns its internal weights and biases from this data. This is where the heavy lifting of learning happens. Validation set. This is the data used to evaluate the performance of each trained model during the tuning process and, most importantly, to select the best set of hyperparameters. Crucially, the model never sees this data during its own training phase for a given hyperparameter set. It's an independent data set used solely for hyperparameter selection and maybe for things like early stopping. It acts as a kind of practice exam for your model settings, test set. This is the holy grail of data, right? The completely held out data that is not touched at all during any part of the training or hyperparameter tuning phases. It's kept pristine and unseen.
Completely separate.
Completely separate. It's used only for the final, unbiased evaluation of the chosen best model on truly unseen data. This provides the most honest, real-world estimate of how your model will perform once deployed. If you peek at the test set during tuning, even accidentally, risk data leakage, inadvertently biasing your hyperparameter choices towards your test set, which leads to an artificially optimistic performance estimate. Bad practice. Let's walk through the robust 5-step HPT process, maybe illustrating it with our housing prediction task. This is really the blueprint for doing it right. 1. Divide data. First, you take your entire initial available data set and rigorously split it. Typically, you'll initially partition a large chunk, say 80%, into what you'll call your training plus validation data, and the remaining portion, for example 20%, becomes your completely separate, pristine test set. Then from that training plus validation portion, you'll further divide it into your working training set and validation set for the tuning process itself. Maybe a common split for initial modeling might be 70% for training, 10% for validation, and 20% for the final test set. 2. Train models in parallel. Now, for each unique combination of hyperparameter values you want to try, you examine degree 2, alpha 0.1, then degree 3, alpha 0.1, and so on. You train a separate, distinct model. Each of these models is trained only on the designated training set from step 1. This process can be computationally intensive, obviously, as you might be training hundreds or even thousands of models, so it's common practice to parallelize it. In scikit-learn, you can often set njobs1 within your grid search CV or randomized search CV to utilize all available CPU cores, making it dramatically faster. A helpful practical tip here is also to set something like error score 0 or NP not nan if certain extreme hyperparameter combinations might lead to training failures. This prevents the entire search from crashing and allows you to analyze where things went wrong. 3. Evaluate on validation set and select best. Once all these numerous models are trained, you evaluate the performance of each model on the dedicated validation set. You compare their scores using your chosen metric, like MAE, and the hyperparameter combination that yields the absolute best performance score on the validation set is deemed the best set of hyperparameters. This is your guiding star for what works well for truly unseen data within the HPT process. This step is about identifying the model configuration that generalizes best. 4. Retrain final model. Okay, after identifying that optimal set of hyperparameters, you typically combine the original training set and the validation set to form a single larger dataset.
Why combine them now?
Because you want your final, chosen model to learn from as much data as possible using those optimal settings you just found, maximizing its exposure to diverse patterns before the final test. You then retrain the model one last time using this combined larger dataset and the best hyperparameters you discovered in the previous step. This ensures your final model benefits from the broadest possible learning experience. 5. Evaluate on test set. Finally, and this is the absolute moment of truth, you evaluate this final model on the completely untouched, unseen test set that you put aside way back in step 1. The result you get here is your most honest, unbiased estimate of how the model will perform in the real world on truly new, never-before-seen data. This is the metric you report to stakeholders, the one that gives you confidence in your model's generalizability. If this score is good, you have solid evidence that your model is robust.
That's a super clear breakdown of a critical, but often, kind of messy process. It brings real structure to what can feel like a dizzying array of choices. So how does scikit-learn, our go-to machine learning library, actually help us implement this systematic search? Are there specific ready-made tools that handle all this data splitting, training, and evaluating for us?
Yes, absolutely. Scikit-learn provides 2 powerful, generic, and very widely used approaches for hyperparameter tuning that automate much of this rigorous process, including the cross-validation part internally. Grid search CV, this method is the brute force champion, you could say. It exhaustively tries every single possible combination of specified hyperparameter values within a grid that you define.
Like checking every square on a chessboard.
Exactly like that. Think of it like being a meticulous artisan trying to create the perfect blend of ingredients, and you exhaustively try every single conceivable ratio to find the absolute ideal. The pros are that it guarantees finding the absolute best combination within the defined grid of values you provide. It's thorough, leaves no stone unturned within that grid. However, the cons are significant. It can be computationally very expensive, especially if you have many hyperparameters or a large number of values to try for each. This leads to what's called a combinatorial explosion.
Right, the number of models blows up fast.
It really does. If you have 3 hyperparameters and you want to try 10 values for each, that's 10 there's 1,000 models to train. And that's often multiplied by the number of cross-validation folds. This quadratic or even cubic growth is why grid search CV quickly becomes entirely impractical once your parameter space gets large. In our California housing example, we might use grid search CV to find the best poly degree for polynomial features, maybe trying degrees from 1 to 5. It often confirmed that for our data, degree 2 was optimal, as beyond that point, the test error, estimated via cross-validation, started to increase, signaling overfitting rather than better generalization. Randomized search CV. In contrast, randomized search CV takes a more pragmatic approach. Instead of checking every combination, it samples a fixed number of candidate hyperparameter combinations from a specified distribution or list of values, rather than just explicit grid points.
So it's more like randomly dropping pins on the chessboard.
That's a great analogy, yes. But you decide how many pins to drop, meaning you control your computational budget via the niter parameter. The pros are substantial. It's often dramatically faster than grid search CV because you limit the number of trials. Crucially, research and lots of practical experience has shown it can often find very good solutions much faster than grid search CV by exploring the parameter space more broadly, rather than just systematically checking neighboring points in a rigid grid. The downside is it's not guaranteed to find the absolute best combination if the number of iterations niter is too low, or if your random sampling happens to miss critical regions of the parameter space. We used randomized search CV to tune the SGD regressor for our California housing data, exploring parameters like polydegree, different learning rate strategies, constant adaptive inverse scaling, all one ratio for ElasticNet, ATIO, the initial learning rate, and POWERT for the inverse scaling learning rate schedule. This allowed us to efficiently explore a much wider range of hyperparameter values without the potentially prohibitive cost of an exhaustive grid search. Beyond these generic methods, which are incredibly versatile for some specific models, scikit-learn offers model-specific HPT or shortcut methods. These are highly optimized versions, such as Lasso CV, Ridge CV, and ElasticNet CV. The concept here is that these models are internally designed to efficiently perform cross-validation for a range of specific parameters, usually the regularization parameter alpha, almost as efficiently as fitting just a single model.
Oh, so they have built-in tuning for alpha.
Exactly. For example, Ridge CV can very quickly find the best alpha value for ridge regression by trying a predefined list of alphas, or letting it determine a range, and leveraging internal optimizations that wouldn't be possible with a generic grid search CV layered on top of a standard ridge model. This provides a very efficient way to tune specific regularization parameters without setting up a full grid search CV. You'd use these when you know you want to tune that specific parameter for that specific model because they offer a significant speed advantage.
That's incredibly powerful, having options ranging from exhaustive grid searches to intelligent random sampling, and even these model-specific shortcuts. We've gone from basic linear assumptions to sophisticated polynomial forms, controlled their complexity with regularization, and now we know how to systematically fine-tune every knob and dial for optimal performance. We've built these models carefully, step by step, but how do they actually stand up to scrutiny? After all that meticulous work, the big reveal, how do these different models actually stack up against each other on truly unseen data? What's the bottom line? This is it, isn't it? The moment of truth. After carefully exploring our data, building foundational models, elevating them with polynomial features and regularization, and then meticulously fine-tuning their hyperparameters, we arrive at the culmination of our deep dive. This is where we finally see how our carefully chosen and diligently tuned models perform on data they have never seen before, our true test set. This performance evaluation is the ultimate arbiter, the real-world validation that tells us if our model truly generalizes and is, ready for potential real-world application.
Precisely. The importance of the true test set just cannot be overstated. I know I've said it before, but I want to emphasize this one last time because it's so critical. This data was completely held out during all stages of training and hyperparameter tuning. Our models have had zero prior exposure to it. Evaluating on this set provides the most unbiased, the most honest estimate of real-world performance. It tells us if our model has genuinely learned patterns that generalize to new situations, or if it's simply memorized the training data's quirks. This is the real measure of true predictive power. For our comparison, the primary performance metric we're focusing on is the mean absolute error, MAE. Just to remind everyone, MAE measures the average magnitude of the errors in a set of predictions without considering their direction, whether they were too high or too low. In simpler terms, it tells us, on average, how far off our predictions are from the actual values expressed to the original units. Since our target variable, median house value, is in units of $100,000, an MAE of, say, 0.27 means our predictions are, on average, off by $27,000. $0.27 times $100,000. It's a pretty intuitive and easily interpretable metric that gives us a direct sense of the magnitude of our errors.
Okay, got it. MAE in hundreds of thousands of dollars. So let's go model by model and see the results on our untouched test set. How did our journey from simple to sophisticated actually pay off? What were the numbers telling us?
All right, let's break down the model-by-model performance review based on the mean absolute error on that crucial true test set, and maybe discuss what each result signifies. Baseline, dummy regressor. Okay, this is our absolute simplest model, serving as our rock-bottom benchmark. It merely predicts the mean of the training labels for every single instance, basically guessing the average house price every time, regardless of the features. Its MAE was around 0.53.
So $53,000 off just by guessing the average.
Exactly. This is our starting point. Any useful model must do significantly better than this purely naive guess. Linear regression, normal equation. Our first actual model solved the direct normal equation, brought the MAE down considerably to approximately 0.32.
Okay, $32,000 error. Yeah. Much better.
Yeah, a significant improvement over the baseline, almost a 40% reduction in error. It clearly shows that even a basic linear relationship captures some of the fundamental patterns in the California housing data. However, as we discussed, there was clearly still room to grow, as this still meant an average error of $32,000, indicating that underfitting the model was too simple to fully grasp the nuances. SGD regressor, tuned with randomized search CV. After thorough tuning with randomized search CV, where we explored various learning rates, penalty types like ElasticNet, and even polynomial degrees within the SGD framework, our SGD regressor achieved an MAE of roughly 0.31.
Ooh, slightly better again. $31,000 error.
Just slightly better than the normal equation approach. This really showcases the power of fine-tuning iterative methods. It proves how SGD, despite maybe its initial complexity and setup, can be optimized to perform very competitively, especially on large datasets where the normal equation becomes computationally impractical. The slight improvement here tells us that iteration and careful tuning can sometimes eke out those marginal gains. Polynomial regression, degree of 2, untuned alpha for regularization. Now, introducing polynomial features was a true game changer. With a degree of 2, and before extensively tuning any regularization parameters, the MAE dropped strongly to around 0.28.
Okay, down to $28,000 error. That's another good jump.
It was a substantial reduction, yeah. It clearly demonstrated the undeniable value of modeling the nonlinear relationships present in the California housing data. It was evident that house prices don't just increase linearly with income or age, for example, but might have accelerating or decelerating returns or complex interactions between features. This model finally started drawing with more than just straight lines. Lasso regression, tuned with grid search CV optimal degree 3. Our lasso model, which incorporates that L1 regularization for feature selection and was meticulously tuned using grid search CV, which interestingly found an optimal polynomial degree of 3 for this specific setup, also achieved an MAE of approximately 0.28.
Same as the polynomial one.
Pretty much identical in this case, yeah.
Right.
Very competitive. It showcases Lasso's powerful ability to potentially simplify models by zeroing out less important feature weights while still handling the underlying complexity through polynomial transformations. This means it offers both strong predictive power and potentially more interpretability by telling us which features contribute most significantly. Ridge regression, tuned with grid search CV optimal degree 2. And finally, our ridge regression model, also meticulously tuned with grid search CV, which found an optimal polynomial degree of 2 and an optimal alpha value for regularization, emerged as the overall best performer in this comprehensive comparison. It achieved an impressive MAE of approximately 0.27.
Wow. Okay, so ridge regression came out on top.
Yeah.
Just barely, but still the winner. An average error of $27,000. That's a significant achievement compared to where we started at $53,000. Why do you think ridge performed the best out of all these sophisticated models in the end? What was its secret sauce? Maybe that perfect blend?
Well, Ridge's success on this specific dataset, achieving that 0.27 MAE, can likely be attributed to its ability to strike a truly superior balance, I think. It effectively leverages the expressive power of polynomial features, degree 2 in this case, to fit the intricate nonlinearities in the data, which we identified as crucial early on when our basic linear models underperformed. But crucially, it combines this flexibility with the gentle yet firm hand of L2 regularization. This L2 penalty prevents the model from becoming overly complex and overfitting to the training data's noise. It nudges the coefficients towards 0 without completely eliminating them, like Lasso might, which means it potentially retains the influence of all relevant features while still ensuring that the model generalizes remarkably well to unseen data. It essentially provides enough flexibility to capture the intricate relationships without getting too entangled in the noise of the training data. This delicate balance between model complexity and regularization is often the key to building robust, real-world models that perform reliably. And you know what you've just seen, this methodical progression from a simple baseline model to sophisticated, regularized, and meticulously tuned polynomial models. It's not just an academic exercise we went through. It really is a standard, proven template for approaching real-world machine learning problems. It emphasizes starting simple, truly understanding the limitations of basic models like underfitting, carefully increasing complexity when needed, like using polynomial features, strategically managing that increased complexity to prevent issues like overfitting through regularization, and then optimizing relentlessly via hyperparameter tuning to get the best possible generalizable performance. This systematic, iterative approach is really how professional data scientists tackle prediction challenges every day. An average error of $27,000 on median housing prices for a block group, especially considering that $500,000 truncation point we discussed, is actually a pretty strong result. For a large-scale real estate analytics platform or even a city planner, this level of accuracy could be incredibly valuable for understanding market trends and making informed decisions.
So ridge regression emerged as our champion model for predicting California housing prices, achieving that average absolute error of just $27,000 for each block group's median house value. That's a huge leap in accuracy and predictive power from our initial baselines. demonstrating the profound impact of thoughtful model design and meticulous tuning. #tag outro.
Yeah, this deep dive has really shown us the incredible power and precision machine learning models can achieve when applied thoughtfully. We've seen how, by combining raw data with sophisticated techniques and careful optimization, we can predict complex real-world phenomena like housing prices with remarkable accuracy. But this journey also brings to mind maybe a broader question for us to think about. Beyond just accuracy, how do we continually ensure that the models we build are not just performant today, but also robust to unexpected changes in the real world tomorrow? Things like sudden economic shifts or new market dynamics emerging. The best models aren't just accurate, they're resilient and adaptable over time.
That's a really compelling thought to end on. We've journeyed today from raw numbers and seemingly disparate attributes to sophisticated predictive models. We've explored the immense power of data exploration, the foundational nuances of linear regression, the magic, maybe, of polynomial features and regularization, and the absolute necessity of systematic hyperparameter tuning. You hopefully now have a comprehensive understanding of how all these intricate pieces fit together to solve a real-world prediction challenge, from the initial question all the way to the final optimized model. The journey of discovery, of course, never truly ends. We hope this deep dive leaves you not just well-informed, but also incredibly curious to explore the fascinating, ever-evolving world of machine learning even further. Until next time, keep digging for those insights.